Yeah, if we have related questions to anything I do, jump in. If you have questions that we don't go anywhere close to, just save them for the end. If you absolutely have to go and you want to get a question in, yeah, well, this is informal, but still a lecture time. So I assume you have all found this set of slides. I did post these, right? Again, I'm going to be admitting people right and left here for a while. Okay, so some of these are there to remind you their topic. Let me get something to take notes with as we go. Okay, so some of these, like this slide, I don't think we need to do anything about it. I mean, if they're questions, they're questions. I'd love to answer them. But, you know, I think you guys know what it is. The only thing that I can think of is that amides are NH2 primary, NH something secondary, and no H's tertiary. Okay. Okay, you just need to learn the names of the first 5. Okay. Although I give you flexibility, you should be able to name them IUPAC or using these common names. And the common names are the ones you're going to tend to find most for these in a lot of settings. Common names don't use numbers, they use letters, and they're offset. The IUPAC names are just a continuation of the patterns you've been learning. You know, each one is a lot of deja vu, but occasionally with some new detail. Okay, and you know, adding substituents, which is kind of what these examples are, you know how to do that. Just do it the same way. Just to give an example, 4-phenylbutanol, if carbonyl weren't there, 4-phenylbutanoic acid. You know, you see the pattern, it makes it very doable. Okay, diacids. We have discussed each of these, except for glutaric, in other contexts. They're just all worth knowing. Maleic and phthalic acid, again, appear in the rest of Orgo 2. Dicarboxylic acids, no secret. Esters, instead of just going through it all again, everybody got the esters somewhat straight? They're a little trickier for some students, but they're just a 2-part name. Everybody follow the naming of this compound. I'd much more likely have you draw that than name it. The harder the question, the more likely you're going to go the easy direction. Okay, amides, they use the same convention as amines for designating what's on the nitrogen. Nitriles, carboxylic acids. Okay, we went through this. Acid strength, I think, is pretty straightforward. Formic acid, you can call it a curiosity because I don't know a hard explanation for that. Acetic acid is default. Down here, benzoic acid, sp squared, a little induction. And going down the list, there's more induction. The the dicarboxylic acids that require a little more thinking. Adipic acid is got 2 pKa's because there's 2 acids and we have to, that's why we treat with them. That's the way it ends up. And it ends up giving 2 numbers, even though you certainly could make a very convincing argument that each carboxylic acid behaves just like acetic acid. So this is somewhat of a result of the formal way we deal with this. Oxalic acid is a strange one. So lots of induction from the unionized part to the ionized part. That gives it a very low pKa for a carboxylic acid. And the other one, I don't have a good explanation, but it's a little lower than you would expect. You'd expect it to be higher. The only reason to talk about this is to convince you that esters have lower boiling points than ketones. Because it's offsetting dipoles. The extra oxygen doesn't make it more, it makes it less. So here's the order. I'm not really worried about amines here, but they would come around the esters. But this is a fairly simple sequence. Most important thing about amides in terms of their properties and in terms of their appearance in biochemistry, biology, peptides and all that, huge dipoles. And that slower rotation about the apparent single bond. Let's see, let me mute. There we go. So this just summarizes that solubility in water is a lot more boring. Any good hydrogen bonding interaction is as good as any other. Excuse me. Okay. Okay, this is for your contemplation, of course. This is the order, and if you look at it, you'll notice interactions tend to be overlapping. I should put the amines on here, too late. Okay, this is review. I'm not going to do all of the mechanisms for all the derivatives of carboxylic acids. It's a bit much this semester, but the top line, you can think of that as the base catalyzed hydrolysis of an ester. The bottom, the acid catalyzed hydrolysis of an ester, as an example, but it's generic pattern. Okay, so here we're just applying with the variations needed. So you can consider this a must-know slide. The quintessential acid catalyzed interconversion of carboxylic acids and derivatives, acids and esters. Okay, I emphasize that quite a bit. Again, the hydrolysis of esters is backwards from the formation under acidic conditions. Base hydrolysis is trivial, but let me emphasize what I've just selected is part of the base catalyzed hydrolysis of an ester. The initial product is not the carboxylic acid. It occurs only transiently in the flask. End of the reaction, you have all carboxylate. We can leave it. If I ask for this mechanism, you can leave it that way. If I want you to reprotonate it, I will separate that. It's actually a separate step. You have to add the acid to do that. Amides, just how to make them from various precursors. So here for the acid and the ester. I've removed all of the discussion of, hey, what's wrong with this step? What's the better way? This is just a generic way to show it. Anhydrides and acid chlorides. I've improved some of these slides. Anhydrides very often, as a rule, include pyridine. Acid chlorides, as a rule, include triethylamine. So I just put down a set of the options as standard choice. Hydrolysis is tough, but works under acid and base. Okay, so again, here at the bottom, I discussed, this step, the middle, with the loss of the negative nitrogen. I discussed other perspectives of that. We're going to keep it simple. We're going to keep with the textbooks. Hydrolysis of nitriles is very straightforward. Protonate, water attacks, rearrange the protons. Base attacks, rearrange the protonate, rearrange the protons. Hydrogens. Okay, so this is review from previous chapter, making aldehydes. So all this is captured because it's part of this chapter too. Dival reduction of esters. Decarboxylation, again, it's here, but it's more important in the next chapter. I just put down the two most typical examples. PET, your Coke bottle, whatever, soda bottle, water bottles, and nylon 66. We use it to make nylons. Okay, so it's important just to be aware of these in general. So it's a polyester because it's an ester. Polyamide, it's an amide. Okay, and this is just for you to think this through. For every arrow, you should be able to put down something about reagents, conditions. Okay, pyridine is not just a base. It reacts fairly rapidly with acid chlorides and hydrides to make the species shown. So that would be the intermediate in the mechanism. No questions. I'll get to lots of problems, hopefully. Okay. I hope you all understood this. Ester exchange, I need to add a slide because I thought I had it in here. Ester exchange is used to make biodiesel. We'll just leave it at that. I mean, it's not testing, but it's used in huge scale to convert triglycerides into esters of fatty acids, and it's biodiesel. And actually, there's an Orgo lab I've seen where people make their own biodiesel. Okay, DCC, another carbodiamides, specialized coupling reagents. The mechanism looks very new, but if you think of it right, it's not hard. So let me go through that. Nitrogen has a lone pair. Think of this as a funny carbonyl. So you want to activate it, you protonate it. And now a nucleophile can attack the carbon. Okay, that is now an activated carboxylic acid derivative. So now the nitrogen can attack the carbonyl group, and you have this leaving group, and then it's just rearrange your protons. So it's really just knowing how to get started for the most part. In a mechanism, you can just leave this alone, what's left of the reagent. Okay, now for the main show, of course. How many people do I have? 51. As good as class. Okay, so that's there. Got to know about enols, how to go back and forth between keto and enol form. Enol content, you have to know it varies and what might favor it. You should be able to rank at least the ones going down the left. Ketone, aldehyde, ester, and amide in terms of acidity, because it has a significant impact on chemistry you can do with them. Mechanism of acid catalyzed bromination. Very little fundamentally new here. So here's examples. And of course, selectivity is a problem if both sides can brominate or chlorinate. Excuse me. This is more a synthetic, more knowledge of reactions and how they're used, not of the underlying mechanism. So here you make the acid bromide, and that will then brominate under those conditions. And then that intermediate, shown at the bottom right, can be hydrolyzed or react with alcohol or react with amines. So this slide is about making things. What do you make them from? What can you make it into? Okay, I'm not going to ask you to explain why showing the mechanism here where the bromine is X'd out. I won't ask you to explain why. That is no simplification to the point of nonsense. You need to know you can't stop. You get a mess or you go all the way. If you can put 3 halogens on there, you're going to do the iodoform reaction. And we can informally call any halogen the iodoform reaction. So the triiodo methyl ketones basically act like esters because you've got a good enough leaving group here. Chloroform itself is about as acidic as ethyl acetate for the curious, about 25 pK. Okay, getting into more modern chemistry is using LDA. This chemistry came around about 1970, I think. I may have said that in class. While I was in middle school or high school. Okay, so this is deprotonated, and these enolates can be used for all sorts of things. Here we're using a source of bromine to make mono alpha bromo ketones under basic conditions. Okay, enolates can be alkylated. I'm only showing you relatively easy examples. You know, basically primary or methyl, which is easier. Okay, you go to secondary, you start getting too much elimination. And that's where we got into the stabilized enolates. So now you have a less basic, still nucleophilic enough anion. You can react with a secondary alkyl halide, and then you get rid of the carboxylic acid. Okay. If there are any questions on these, you can stop me.
I have a question.
Absolutely.
So for a few slides back,
The system is very bad at telling me who you are.
hi, I'm Genesis.
Okay, Genesis.
Okay, so I have a question with when we're doing bromination. For the mechanism, do we use BRX only for monobromination, or is that also when we're making bromoform?
Oh, no, you use BRX or IX. You know, the fundamental chemistry is bromine. BR2 does not exist if there's hydroxide around.
Okay, got it. Thank you.
Just does not. It's I don't know where these things come from. I haven't checked my textbook. It's in my office, not home, but I'll have to see what it does. It may do the same thing, but you know, nonsense is nonsense.
Okay, thank you.
I mean, if I teach you a mechanism the way it's shown and we know it's not right, I always say so. I tell you when I'm lying. Okay, so here we're using an ester ketone. And then the ester we get rid of. The same thing happens with a diester. And we can only get rid of one ester. And why would we want to not keep one? Okay, so these things can get fancier. This isn't ultimately harder once you learn the basics well enough. Enamines are a little more minor topic, but they are, you know, widely used for some chemistry. Okay, so they react with electrophiles. Mechanisms are somewhat straightforward, even though there are some counterintuitive steps, like protonating an oxygen in the presence of a nitrogen. The examples, so they can be alkylated, they can be acylated, and we saw one other use. So these ester ketones can be used to make diketones by clever choice of the reaction conditions. You can acylate it and then get rid of the ester. So it's the same thing as the acetoacetic ester synthesis for alkylation, but you're just acylating it. So it's just another electrophile that ends up in a different product now. Age-old reaction is a Claisen condensation. So the anion of the ester is a nucleophile, and the same ester is the electrophile. The problem with one limitation, it's not a problem, it's a limitation, is you can't make a quaternary center. And we talked about why that is. It has to do mostly with sterics. And then, you know, things can be done in all sorts of different ways. It's your imagination's a limit. Intramolecular, not a big deal, I hope. Crossed Claisen, You have to think through it very carefully and run the reaction conditions correctly. But this one is a slam dunk. The middle one here requires nothing other than throwing them in a flask and, stopping on time. The last one requires special reaction conditions as indicated. Okay. You can take an ester and make a diester for whatever use you want, using things like diethyl carbonate. Use diethyl oxalate, and now we're getting much more fancy group of cluster of functional groups. And you can do across ketone ester, ketone more acidic, reaction with another ketone disfavored by the steric hindrance of it, reaction with the ester, irreversible due to deprotonation. Okay. And this bottom reaction is a great example. If you know what's on this slide at this point, and I show you this, where's it going to deprotonate? Next to the ketone. Where's it going to react? Oh, the ester. It should be that type of thinking. Now, there's a choice here because the ketone can deprotonate on either side. So you can make the anion here, 1, 2, 3, 4, 5. That's good. You can make the anion here, 1, 2, 3, 4, 5, 6, 7. 5 and 6 are the easiest to make, they win. And then the classic aldol.
Hi, sorry, I have another quick question.
Oh, please,
Genesis
nobody's
again.
asking questions. I'm feeling like I'm here alone.
Okay, on the previous slide, we go back. I just want to make sure for clarity, is the ethanol and methanol here used to reprotonate what's being made?
Actually, I'm not showing reprotonation, so think about it yourself. Methoxide or methanol has a pK of around 17, 16.
Yes.
And you have a diketone here with a pK of 9. So under the reaction conditions, it's the anion in the flask.
Okay.
And so you need to add acid at the end to protonate it. Again, that's usually just assumed.
Okay, yes, that was my question. Thank you.
Yeah, I mean, textbooks are often very keen to add all that detail, but I would rather assume it because any publication you look at, they're going to do it. And I try to present this stuff the way you would see it in a little publication. Summer research job, read this. Yeah, I don't want everything to look new to you, different.
Okay, yes, I noticed in the textbook they use H3O plus as the
Yeah,
acid
they
workup.
just say, don't forget, you got to protonate it.
Yeah, thanks.
Okay, so under base conditions, you can get the aldol, but you can't with a ketone. A ketone isn't stable enough. You have to dehydrate it to get the enone. And the easiest way to do that is under acid anyway. So under acid conditions, the ketone, again, does not make the aldol product, the ketone, to be called a ketol, but that, I don't know if that's a word. Ooh, it doesn't like my spelling. Oh well. So under acid, they always dehydrate. I don't know if I actually have enough on this. If you do this first reaction under acid, you're going to get double bond. It'll dehydrate. Okay, so here's just examples. Again, you can do them crossed two different ones if you're clever enough. And then if you have two possible enolates, yeah, you got a problem. So you can do this with LDA and be selective about it, at least as selective as LDA is. Okay, and then the last reaction, this is conceptual. This is to help you think about it. But enones, an enone is a single function group. It's not one of the basic function groups. It's a combination, but it has to be considered a single function group. Methyl lithium or methyl grignard is going to make the tertiary alcohol. Methyl lithium dimethyl cuprate is going to make a ketone with a methyl group introduced to the double bond gone. Okay, so we can do arrow pushing to show where the bonds are made, but for the cuprate, it doesn't, the copper compound, it doesn't go that way. Okay, and just a couple of examples. And here's just showing that the cuprate anion, you can go ahead and alkylate it. So, okay. And then the conjugate additions. So softer anions. The ethyl group on a copper is softer than the vinyl because of the covalent character. Here, a stabilized enolate is a soft anion. I keep getting people coming still and then people leaving. Anyway, excuse my muttering. And so this undergoes conjugate addition. The hard anions can undergo conjugate addition. In this case, I'm pretty certain I didn't mention lecture. The anion here, the enolate anion, can attack the carbonyl, but that's reversible. And so this is the net reaction that happens. I don't want, this is too late in the semester. This is too challenging a chapter to get too picky, but this is not a preference for site of attack, but making the most stable product. Okay, and just an example with a nitrile, just for the heck of it. The mechanism of the reaction with diiodomethane or methylene iodide combines a enolate alkylation and then what's called a beta elimination. You make the anion and kick out the iodide, and then a conjugate addition. And then if you keep going, you do the hydrolysis and decarboxylation. So this slide contains a lot of what we've done in this chapter. Okay, and then there's a Robinson annulation. Okay, multi-step. You got to be a little bit careful. Keep track of the bonds. We can go through a practice question on this if I find one in what I've got. Be a good one to practice on. This one shows, this is called methyl vinyl ketone. And it's kind of easy because 1, 2, 3, 4, 1, 2, 3, 4. Notice the ketone becomes the carbon-carbon double bond, and the ketone in the methyl vinyl ketone is out here. Here, it seems to be a lot harder. The same pattern, it's just you have this extra methyl group. Notice it's on the carbon next to the ketone. It ends up on the carbon next to the ketone. It kind of went along for the ride. And then enamines. Yeah, just one more variation of this chemistry to know. So before we go on to the homework, Next on my list, any questions? Should we start with the enolate homework and go to the carboxylic acid derivatives homework, or keep it in regular order, or what's your pleasure, guys?
Can we do the carboxylic?
Absolutely. Oh, I thought I'd opened the key. This isn't the key. Okay, I'm assuming that almost everybody has gone through this. At least the first time. One thing I've added, my homework is not just learning basics, but a little more. The little more on this first question is this table. And I quickly refer to this in lectures. If you don't remember it, not a problem. But there are group electronegativities that are quite useful, especially nitro. Nitro group has an electronegativity of 3.4. You can't use the electronegative of nitrogen. It's not a normal nitrogen. So that's one where this is absolutely crucial. Some of the others, yeah, vary. But trichloromethyl, you go to electronegativity of that. The carbon doesn't have the electronegativity in the table for carbon. Okay, so methyl group is 2.3. Ditrichloromethyl is a lot more. Okay, so this is just using that for two of these, and the other two are the halogens. Okay, jump into questions. Don't be shy. I expect at least one person to totally embarrass themselves today by asking a question and then say, oh, I know, why'd I ask that? Okay, are we good on naming? We need some practice. Oh, that's what's happening. Let me point out the 6-member ring here with the acid and the methoxy group. Cis, the two substituents of the ring are cis. People seem to have forgotten that on the last exam. Okay, we good on 4? We need to go through it. Question, valeric acid, you don't have to. Valeric anhydride, there's all these acids have common names and IUPAC names. They're called common names because they're commonly used even now. I mean, to have you learn cumene and isocumene and all those common names that aren't really used that much, nah. But valeric acid, yeah. Valeric acid is borderline, but butyric is widely used. Oh, down here, that is just, who is that? I don't see the name. This is just saying two of these. In parentheses, two. It's using parentheses as if we were in a molecular formula or a line formula. So everything in the parentheses, there's two of those attached to the oxygen. It makes it a symmetrical anhydride. Okay, well, I can go down to 8, but let's get down there a little bit. So everybody's good on these sequences in 4. It's easy to just see them and say, okay, but could you write them down again? Oh yeah, Ariana, I noticed you're bouncing in and out. Okay, let's go to ChemDraw. That'll make that easy. I don't know if the student ChemDraw has this. I'd like to see the student ChemDraw sometime. Structure to name. And for the person that asked about valerate, I don't know if it would do it, but it used butyrate here. The naming system, we can find out. So I can click, oh, it switched to pentanoate. Yeah, I'm not surprised at all. Okay, so I'm having trouble with my fingers today. There we go. Okay, I've just switched everything around. So I wish I could get this to more flexible. Stick with me. I want to try one more thing. Oh, not what I wanted. Oh, good. Got it. Okay. So I have methyl alcohol making an ester with pentanoic acid. And so the methyl of methylpentanoate can be thought of as coming from the methyl in methyl alcohol. But that's the same methyl if I can. It's not continuing the name. Okay, I'm showing it here with the alcohol. Okay, I'm showing it here with the alcohol, but the methyl occurs in methyl chloride. The methyl occurs in the less common name methylbenzene. It's the methyl as in a substituent. Okay, so that methyl substituent name occurs in the name of the ester. So there's the so it's that methyl that's a substituent that is the methyl used in the ester name. And then the pentanoic acid changes form to pentanoate. Okay, was this Jennison sex just again, or is it someone else? Excuse me. Well, it doesn't matter. The pentanoate is a form like a salt. I said this in lecture as well. So this is sodium pentanoate, which is a salt. This is methyl pentanoate. It's not a salt, but it carries that form for historical reasons. Okay, now if I change this, now it's 3-methyl pentanoate to go with 3-methyl pentanoic acid. Okay, so the name of the ester changes the same way the name in the acid would. If I change this now, come on, it's lost a link with a name. Yeah, it's going to keep the other name, other form. And so this isopropyl alcohol becomes isopropyl 3-methyl pentanoate. Okay, does that help? Oh, it's Ariana that asked. And you know, it can get a lot more complicated looking. Oops. Wanted it. But this is 2-phenylacetic acid. This is isopropyl 2-phenylacetate. Now, this is a very formal IUPAC name, but this is what it would be. 1-methoxy propane 2-il alcohol, 1-methoxy propane 2-il phenylacetate. I'm doing this to show you the pattern continues. This does not belong on an exam. Sorry. Compound compound substituent forms like this just aren't going to go on exam. Oh, let me change it. That I would put an exam. Oops. 1-methoxy ethyl alcohol. Oh, I'm sorry. I have to change that myself. It won't change it. 2-methoxy ethyl alcohol, 2-methoxy ethyl 2-phenyl acetate. We good, Ariana? Yeah, I put these schemes on here. These are a great way to practice and a great way to review and know all your reactions. Seven is not so much of, oh, I got a hand up.
Hi, I think it's me.
Oh, Erica. Yeah, I've got the lack of pictures hidden, so I can't see the hands raised. So Erica,
Okay, I have a question about number 4.
please.
And I think a couple other people might have questions about number 4 in the chat.
People have questions. They're just shy.
I have a question about the oxidative cleavage of an alkene.
Yeah.
So I'm not sure if I'm remembering correctly, but can you oxidate that completely with potassium permanganate?
Yep, that's an alternative. The answers here are certainly not comprehensive.
Okay, gotcha. Thank you.
Yeah, so that would make the carboxylic acid directly. Yeah.
Okay, thank you.
Yeah, I mean, anything that works gets credit. Every now and then I get the strangest answer in an exam, and I think, where the heck did they learn that? It works. People learn things off the internet, and I got to give them credit for it. Okay, so 7 is the type of thing you can do as a learning exercise, whether it's on the homework or not. Summarizing things, that's what this is. Okay, 8, there was a question. Okay, okay, the cold and careful is a detail I wouldn't require you to put down if I asked for the reagent. But if you're careless of dibal, you get complete reduction. Has to be carefully kept cold, or it over reduces. So that's the only reason that's there. Okay, and then I think naming esters. Question 4, we're backing up to. Okay, so the top it's a simpler one. I think we've addressed that. But ozonolysis just takes off the extra carbon. When you see problems like this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, I'm lost a carbon. So I have to cleave a carbon-carbon bond, here a pi bond, or the double bond. And to do that, ozone. It's fun, it's clean, but permanganate works. And then there's other ways to oxidize the aldehyde, but we know that chromic acid does, because there has to be water there. So that's the easier one. So again, 6, by 6, 7. So on an exam, on a homework assignment, in life, you got a problem, make sure you understand the nature of it before you worry about answering it. Here you got an anticarbon. Okay, so this makes it tricky unless you remember that CN adds a carbon, and the nitrile you get is a derivative of carboxylic acid. Okay, so you got to take the pi bond and reduce it or add something to it, and get a leaving group on the end so you can react with cyanide. So this is a little puzzle. Absolutely. Well, until you've seen it a few times, then you just kind of remember it. So here, hydroboration, give the alcohol, tosylate, there's of course other choices, displace with cyanide, and then hydrolyze it. Okay, Tiana, does that help? Audrey, you have your hand up?
Yes, can you hear me, Professor?
Absolutely.
All right, so it's also about question 4. It's what we have at the very right with the SOCl2 and half an equivalent. I don't understand what that means.
I'm sorry. Very
To the
right.
right,
Yeah.
I don't understand.
I'm sorry. I was
what that
adjusting
does.
my screen. Can you say that again? Very right.
Yeah, the carboxylic acid to the using SOCl2 half an equivalent. What's
If
going on there?
you use an excess, you get nothing but the acid chloride.
Oh, and what's that thing at the bottom? Because when I was looking at it, I don't understand. Is it a carboxylate?
That's the symmetrical anhydride.
Oh,
We have an oxygen with 2 of these acyl groups on it.
oh, okay. I get it. Thank you.
Yep. I am going to call for a very short bio break, whoever needs one. Okay, I'll be right back. I don't know, my self view up, but Omega's here. Okay. She wants this. My mother-in-law came back. I went to the airport and got her yesterday, and the boy, the kitchen smells good. Eight I. Xiao Tong and everybody else think the same thing. The products of I. Don't those look like aldehydes? In a somewhat altered form? These are absolutely not alcohols. I see no alcohol there. Functional groups always, how do I put this context? Okay, this is, if this were an alcohol, that carbon would have only carbons and hydrogens on it. The carbon the OH is on has an oxygen on it. That by default is not an alcohol. It has the appearance of an alcohol. It's not an alcohol, it's an acetal. An acetal is a trivial derivative of an aldehyde. And because this is an intramolecular acetal formation, you can't stop it. I'm sorry, hemiacetal. Yeah, hemiacetal. Dibal, I'm not sure the question from, is it Carol? Piotrowski? Yeah, dibal reduces carbonyl groups. Here it's reducing an ester and stopping, and the explanation for why that stops is on the slide. Okay, 9 is not a really important question by itself. It's just a way for you to think about these things. I gave you 3 choices and 3 reactions and said, match up the reagents. What's the best way? The top one, yeah, Fischer esterification works just fine. You have a basic nitrogen in there, which may cause trouble if you try to make the acid chloride out of this or anhydride. So here, to avoid any stability problems with an acid chloride or anhydride, you just use a Fischer esterification. So the middle one, you have to use an acid chloride or Fischer or anhydride because the Fischer has been taken. You know, there's a matching question. So here, if you use the anhydride, you got a significant piece there. Somebody worked hard to make that. You can waste half of it. So here it makes sense to use an acid chloride. The last one, you're making an ester, a simple acetate. Hey, use the anhydride. No reason to get fancier. Ten is my way of helping you get a head start at reviewing for the final exam, but most of it is in this chapter, not all of it, of course. And again, 11 is helping you get ready for the final exam. But there's a lot of chemistry from this chapter. And then some mechanism practice. Okay. Any more questions here? Or should we get on to the last chapter? Okay, so these are all good mechanism practice. And there may be variations of the way this could be done. I didn't consider all reasonable possibilities. Okay, for the last chapter, you should be able to rank, oh, for 12B. Okay, what is it? Yeah, it's just in this step. Here you're under more basic conditions than not. There's nothing really obvious to protonate this. So, you know, you're making a fairly stable cation. So here it's okay. If you protonated this first, because you do have some ammonium in here at times. Yeah, this type of internal one. So you got a lone pair here to kick it out. But just don't use it a leaving group for the SN1, SN2 type reactions, E1, E2. Audrey, you're garbled, Audrey.
I'm sorry, can you hear me better now?
A little bit. Now you're a little garbled.
How about now? Is this better?
Go slowly, I might be able to follow.
Okay, so my question was, initially when I did this, I had the lone pair from the oxygen come down. Why does the lone pair from the nitrogen come down instead?
You know, in this step here,
Near the beginning?
if we focus on this very last step, the bottom
Okay.
corner here, does this have a resonance structure?
Yeah.
Yeah, so the lone pair on oxygen come through, make the nitrogen neutral. And so those two resonance structures are the same structure. So if you show it with the lone pair on oxygen kicking it out, you've shown exactly the same thing. They're both kicking it out at once because of the resulting resonance structure. Isn't that
Okay.
cute?
Okay, thank you.
Yeah, it's shows the problem with localized bonding, right? Which one's kicking it out? They both are. You just have to pick one to show it. It seems like the nitrogen's the right one to show it, but that nitrogen's got its own resonance. So the oxygen might be better, but it's the same thing. Okay, so notice there's 16, there's 10 orders of magnitude here. There's 16 orders of magnitude here, 16 orders of magnitude different between these anions. Huge range. So you got to have a feeling. I mean, the three, 9, 11, and 13, yeah, they're kind of in the same ballpark. And 25 is dramatically the most basic. So, yeah, you got to have an appreciation for that, even if you can't cite numbers. You got to be able to do at least a rough ranking. Practice drawing resin structures, anybody? That'll do it. 3, again, it's just more practice and basic Orgo skills, but in a new context. And notice the first 2. The enols have cis and trans isomers. And the first 2 are the dominant ones. Four is thinking Orgo. With a test coming up, I would see if you can follow this, but I wouldn't freak out about this one, okay? Five is again a mechanism practice. So the acid catalysis can result in an annoying number of steps, but you just go through them. Six, again, is just practice in finding the products. I'm giving you a cross-Claisen condensation that will form all 4 products. Seven, I'm taking a little look at carbohydrate chemistry, but this is certainly important when you don't have carbohydrates. So how do the carbonyl group on this line, how the carbonyl group and the hydroxy group change places? Yeah. You make the enol, you unmake it going the other way. Okay, so again, more practice. And here, just rip it off the products and practice naming. So stop me somehow if you have a question on one of these. Notice on here, it stops there. The carbon bond cleavage in the iodoform doesn't work unless you have 3 halogens on one side. ENF I put in there. So it shows a Wittig reaction. You hydrolyze it and you just move an aldehyde out one. So it's kind of cute, but certainly I don't expect you to remember how that's done. Just see that it's done. Okay, these are all, there's a lot here. I never deny that, but these are all somewhat straightforward. So now 12, you have to supply the reagents. Again, a lot of this is also review for the final. Practice using the malonic acid synthesis. You know, it's a lot of work. But if somebody struggled through all of these transformations and they have the time, you know, repeating these from scratch would certainly help you improve your knowledge. How you know, you might know something, but it's not yes or no, it's how well you know it. So it can help you improve your knowledge. Just a cute. So there's not a lot here unless somebody has a question. I mean, there's a lot here, but not a lot that you would obviously ask about. I had forgotten all the practice in this homework. Have we all had enough? Or do you want some brand new questions? Just a reminder, the last two exam scores were a bit disheartening, especially for the students. I have made this exam much more basic in the types of things I'm asking. I hope you agree with me after you've done it. No more information on exam 4. Just pop one off. I have a book open in front of me just for inspiration. Oops. I've never had good penmanship. I hope you can read it. What's the product? No classes meet on reading day, Xiaotong. This is a very unusual schedule this semester because we have 2 lecture days after reading day, which doesn't make sense. But I have a suspicion why they did that. Yep, you're gonna make the anion. Okay, and then you want to alkylate it, right? You got an alkylating agent? Oh, I'm sorry. Getting overly zealous. And this is a T-butyl group. And the name was correct. With the correction. This book goes beyond what you do. This is the book they use at Cornell. Here's one. That is an oxygen there. Not getting much feedback from you guys. You want to see the answer now? And draw it whenever you think you're ready. Somebody's getting into naming. Yeah, I can forgive you. This is informal setting. I'm to find out where I got it from. Oh, here we go. Yeah. So the product is a dione. So you have to just ignore the extra carbonyl group here. That is very reactive for SN2 chemistry. Alpha to a ketone, you kind of look phthalilic, and yeah, it's more reactive, but you know, it's any reaction that happens on the ketone is not going to be good. So enamines,
Hi, it's Genesis.
Yeah.
Can you draw what happens after step 2?
well,
Just the product. You don't have to actually draw the mechanism or anything like that.
that has two ways to make the enamine. Okay, and because of what we saw, it tends to go what you wouldn't expect. This is going to react. Oops, I went too far. It's single bond. So the enamine will alkylate and it'll make a new enamine. The enamine's regenerated. And then this gets hydrolyzed.
Okay, thank you.
Oops. Okay. Hope so. Okay, retrosynthesis. How are you going to make that 4-member ring? It uses a standard synthesis of ketones we learned in this chapter. It has a name reaction, not a person's name though. A name for the common starting material. So we learned learned a way to make that kind of thing. Yeah, Erica, you can make enolates of sodium hydride. It's kind of slow, but it works. I think I saw that on the page here. Yeah, so everybody else can ignore this just to answer her question with a specific example. and they give the solvent. So giving this plenty of time with potassium hydride and THF can deprotonate and make what is obviously the thermodynamic enolate. Yeah, there are fancier ways to do it, but that works. This is kind of the limit of how much you can do with sodium hydride acting as a base. Okay, for the problem at hand, you need the acetoacetic ester synthesis. Okay, so what's the reaction partner? How you proceed? So that should get everybody a good chance of getting the answer. Yeah, we're almost out of class time. I'm going to make this the last question. So the reaction partner will be that. You're going to get that for the intermediate. And then saponified decarboxylate, you got your methyl cyclobutyl ketone.